Thank you, Matt, and good afternoon, everybody, and welcome to this Technical Tuesday webinar. I hope you're all keeping well, and we mean that when we say that nowadays. So this is another two-person webinar. I am presenting this with my colleague Soki. Just to introduce myself before passing over to Soki, I'm a Senior Architectural Conservation Advisor in Building Conservation and Geospatial Survey, part of the Technical Conservation team at Historic England. I've previously been a Chartered Historic Building Surveyor in private practice, former Technical Secretary of the SPAB, and I joined this organisation in 1997. My career in English Heritage and Historic England has mostly been in overseeing grant aid to historic buildings and heritage at risk work in regional teams. Soki, would you like to say a few words about yourself?
Sure. Thanks, Nikki, and thank you, Matt. I'm Soki Riduvan. I work for the same team as Nikki in Building Conservation and Geospatial Survey. I'm also a Building Conservation Advisor, and my day job is really managing research into the energy efficiency and climate change adaptation for traditional buildings, which incidentally has a lot to do with understanding the moisture behavior of buildings, impacts of interventions, risks of moisture, and moisture assessments.
Thank you, Soki. That's great. Before we make a proper start on the webinar, I'd just like to let you know a bit about the Technical Conservation team. We're a group of technical specialists, including conservators, scientists, and engineers, and we undertake research and provide advice and guidance on technical conservation issues. The first link that Matt is posting in the chat room for you would take you to the main technical advice page on our website, where you can find all our technical advice. All our research reports and PDF guidance documents are free to download from our website, and the second link takes you to the catalogue shown on the right, where they're all listed. Also, I thought you might like to know that we're introducing a technical conservation newsletter, which is planned for the last Tuesday of each month. This will let you know about new technical conservation guidance and publications, or any forthcoming technical conservation training events. If you'd like to add your name to the mailing list and haven't already signed up to a previous webinar, just click yes, and we'll send you the next edition of the newsletter. Just to be clear, this is just for the technical conservation guidance and events, not all Historic England publications or trainings. So we'll give you a couple of seconds to do that. I do realise that some of you may already have signed up at previous webinars. There's no need to do so again, but don't worry if you do it twice. Even if you sign up twice, we'll check the addresses and only send you one email. Okay, so let's focus on the subject in hand, the survey and investigation of damp. So why focus on this as a webinar? Well, because damp is the major cause of defects and material decay in buildings, and survey and investigation are essential first steps in identifying the cause of dampness, understanding the implications on building fabric, and this is also used in planning the programme of action, maintenance or repair. In terms of the format of the webinar, Soki will discuss moisture, damp and the implications of damp, and then I will consider surveying for damp, followed by Soki completing the presentation by focusing on investigation. So, as a start, I'll pass over to Soki, who will introduce the subject of moisture.
Thanks, Nikki. So I'll start our presentation talking briefly about moisture, what is damp, and how moisture interacts with buildings. And these are some of the buildings that I'm working with at the moment. Moisture and damp is a recurring theme in our advisory and research work, from the general care of buildings and dealing with moisture ingress and decay of fabric, to energy efficiency and understanding the hygrothermal behavior of building elements in order to manage condensation and moisture accumulation risks from energy efficiency improvements, and to managing threats and emergencies from flooding resilience and recovery. We must remember that all traditional building materials are hygroscopic as they are semi-porous and therefore contain some inherent moisture. When undertaking moisture measurements, it is important to differentiate between a building in its natural state, that is in equilibrium with the surrounding air, and a building that is suffering from damp. Surprisingly, materials in a dry building can contain a lot of moisture. For example, timber can have between 10 to 20% moisture content, which has reached equilibrium with the surrounding air. Bricks, depending on its material properties, can contain anything up to 5%, but typically maybe about less than 1% for an inner face wall. Cob walls could have anything between 1 to 3%. This is generally not harmful and is not regarded as dampness. It is the material's standing level of moisture equilibrated to the surrounding air. Where it becomes a problem is when there is too much moisture from an active moisture ingress that accumulates over time and causes damage to a building. This is known as the free or capillary moisture content of a material, which indicates the presence of liquid water. There are different regions of moisture storage in hygroscopic porous materials. As most building materials are hygroscopic, they can absorb and release moisture vapor. Inherent moisture that is usually not damaging occurs in the hygroscopic region. Beyond this, in the capillary region, free water is present and a material continues to absorb liquid water by capillary suction. For example, at high humidities, wood will absorb vapor from the air up to 30% moisture content, but fully capillary saturated wood wetted by liquid water may hold double or more times this amount of moisture. Once a material is capillary saturated, it will generally not be able to store any more moisture, which is in the supersaturated region. When a material is oversaturated and no more water can be wicked into the material, and drainage mechanisms, if available, will begin to remove this excess moisture. The effects of damp conditions are numerous, but they are usually the result of condensation, rain penetration, and by what is commonly described as rising damp, by which I mean the upward movement of moisture by capillary action, usually as a result of defective ground and surface drainage systems. These give rise to mold, biological growth, corrosion of metal components, and decay of timber within structures, pest infestation, and physical damage from frost and salts, and dimensional changes causing structural failure and cracking. Other sources of moisture are construction moisture, plumbing leaks, leaky roofs, ground and surface water, contaminating salts, and condensation from occupancy, all of which can be made worse by poor maintenance and inappropriate use of materials for repair. In addition, damage from floodwaters from increased river and tidal levels, contaminants carried into a building by floodwaters, and unfortunately sometimes from our own recovery efforts, will increasingly become more frequent as a result of climate change. Water occurs in three physical states: solid, liquid, and gas. Depending on the temperature and atmospheric pressure, water can change from one state to another, a process called physical phase change. Consideration of moisture risk relates to all the three states, for example, as a gas or vapor, that is evaporation, relative humidity, as a liquid by condensation and absorption, and as a solid with freeze-thaw effects. These are all conditions that all interact and should be considered together. For a moisture-related problem to occur, several conditions must exist. As already discussed, a moisture source must be available. There must be a route for the moisture to travel. The materials involved must be vulnerable to moisture damage, but there also must be a driving force or forces to cause moisture movement. Primary moisture transport mechanisms are, in the increasing order of power, vapor diffusion, which moves water vapor in porous materials from regions of high vapor concentrations to low concentrations, vapor convection of airflow through small openings, and these two mechanisms only account for small amounts of moisture movement, and in most cases they are not of major concern, whereas the next two that I'll just mention deal with liquid water rather than vapor permeability and can cause significant damage. They are capillary suction, which moves liquid water through porous materials The smaller the pores, the more powerful the capillary suction, but slower the flow. And gravity flow, which is the most powerful means of moisture transport, where very large quantities of liquid water can flow downward through openings and cracks, pipes, or air spaces. However, in real life, a combination of transport mechanisms could occur together. Sorry, let me just move the slide on. Understanding how moisture behavior is important, as traditional materials in buildings take up moisture from their surroundings and release it according to environmental conditions. Modern buildings depend upon impermeable barriers to control the movement of moisture and air. Technologies used in modern buildings, such as damp-proof membranes, are inappropriate for traditional buildings, as it inhibits their ability to buffer moisture and heat, which allows them to even out fluctuations in humidity and temperature. However, this equilibrium may be adversely affected when there are changes to the building fabric, or when an active moisture ingress occurs and inappropriate measures are taken to remedy this. This can lead to problems with moisture accumulation, such as fabric damage, and occupants may also experience ill health due to poor indoor air quality. So that ends my brief introduction to moisture.
The Chartered Building Surveyor of the team, the section on surveying fell to me. So I will consider survey and then pass over to Soki, who will consider more the investigation stage of things. So rather than a comprehensive how to survey, I wanted to focus on the thought processes and questioning that needs to be brought to the historic building survey. I'm not, as I said, discussing the equipment that can be used to measure liquid moisture, vapour or hygroscopic moisture, as Soki will cover this. My primary focus is more on the presence of liquid water. How has it got there and what are the implications? As you've seen, we do need to bear in mind during survey, firstly, that the external wall of a building is the buffer from the ever-changing weather outside in the form of sun, rain, wind and temperature change, but also dealing with vapour created inside the building. And secondly, as Soki has explained, the way porous traditional building materials transport water in liquid and vapour. Remembering that it's the thickness of our historic building's external wall that has to deal with liquid water via capillary draw or suction into the surface of the porous materials, and that evaporation is a process of its removal when the external conditions of sun and more particularly wind are favourable, and that in gas form, as water vapour, diffusion is the action transporting the vapour into the surface pores. So, question, how does this information impact our survey and investigation? Moisture content in traditional external walls is not static. Moisture is absorbed, evaporated or diffused in reaction to changes in external and internal environmental conditions on an hour-by-hour, day-by-day, season-by-season basis. So we need to remember that a one-off visit or survey may only capture a tiny picture of this dynamic system. Wall thickness is also important in buffering against outside weather, and the surfaces of the walls are essential to porous material moisture transfer. This is why we should expect, for example, a high moisture reading on the wall surface, higher than in the centre of the wall, or, for example, salts in solution to be drawn towards the external wall surface within water movement, and be present at the surface of the wall as a result. As Soki has explained, in comparing how modern buildings work, this is very different. Modern buildings have the benefit of impervious materials and barriers that keep moisture out of the building from the day they're constructed. You'll be aware, hopefully, that there are two webinars that we have produced by Robin Pender. They're called A Common Sense Approach to Damp, and Robin explained this greatcoat versus Macintosh approach to moisture. Matt hopefully may have the links to this. Robin's a physicist, and she explains the physics behind moisture movement. So, in undertaking a survey, we've also got to consider the impact of inappropriate interventions. Questions a survey should address. Firstly, if there is dampness, what is the source of moisture? Or what defects are there that need addressing to stop the ongoing supply of moisture? And then, how did the building fabric originally transfer moisture, and how is this working now? What's affecting the equilibrium? As Soki explained, that's the balance between the moisture being removed by evaporation and diffusion, keeping up with or balancing out the moisture being taken in to the porous material. What's the condition of the building fabric telling us about the source of damp, and what are the implications of damp on building fabric that can be seen or may be hidden? Survey alone may not be enough, and further investigation may be needed to answer these questions, to understand the form of moisture in a building and the impact on changeable environment. Soki will address this. So, let's turn to the first aspect of our survey, understanding the historical context of the building, or how they built or designed with only porous materials. So, Very Grand Stow is sited on a slightly raised platform. The ground slopes away, allowing water to run away from the building, and the first floor, or piano nobile, houses the state rooms with the expensive furnishings and silk wall hangings, well away from the risk of ground floor damp. Sliding sash windows, being leaky, also provided non-intentional as well as controllable ventilation, and roofs and chimneys were hidden behind parapets, so it was usual to find hidden valley or parapet gutters with rainwater removal out of sight. Conversely, this cottage would not have originally had hard surfaces directly against its walls. The ground is slightly high, there's now that awkward channel, and it does slope towards us. The steep pitched roofs have good overhanging gables and eaves, and jettying of the first floor shelters the ground floor. Windows and doors have drip details at their head, and critically, in dealing with moisture, the lime-washed pargeting or decorative render and lime wash covers the building, but especially note the panels and the timber in the timber frame section is lime washed. In dealing with moisture, the whole surface is porous and working as intended. What next we have to ask is the building's location and environment. What will be the effect of weather? Could there be pollutants in the air? The building with the sea view here does have chlorine salt issues. How much wind or wind-driven rain will it have to face? The orientation of a building is also important. Churches are oriented east-west. The north slope of a roof is often wetter and sheltered by the shadow of the church tower. And as has been pointed out, flooding is an increasing risk that needs to be considered. Looking at the whole building in terms of weathering, the Georgian church portico has its entrance level raised a few steps, and the trees may provide shelter, but beware of those tree roots. They can disrupt below ground drainage or cause localized settlement, resulting in cracks and water entry. There's a parapet gutter hidden by the cornice. Always be skeptical of what you can't see. You need to get underneath and look for signs of damp problems, or more ideally, get into the gutter and check for problems. The Victorian approach to detailing against the effects of weather forces rain to take a tortuous route to get to the ground. Overhangs provide shading and drip details for rain, but look at those junctions between all those different materials that need to be kept weather-tight. In surveying buildings, you need to look at where water may be entering, so it's logical to follow the path rain would take from the roof downwards. So let's do that. Starting with the ridges, ridges need to be soundly bedded with no gaps, and copings, again, need joints that are functioning. Junctions are always a weak point in a roof. In both these pictures, the decision has been taken to use lead to help water shedding. This can minimise loss of worn fabric, but has a visual impact. Lead is a wonderful, malleable material that has been weathering buildings since medieval times. Despite lead theft, it remained the best material for weathering junctions. On this Lake District church, conversely, the water does get in from the lack of overhang at the gables and eaves. Turning to roof slope coverings. To keep water out successfully, the pitch of a roof relates to the material being used. These timber shingles work because of the steepness of the pitch, means that rainfall, encouraged by gravity, falls quickly from their surface. The downward grain of the shingles helps too. The skill of the roofer is always key in making a roof watertight. With non-interlocking roofing, it's the overlap or adequate head and side laps that provide water tightness. Missing tiles or slates need to be replaced, but you also need to think, with missing units, what is directly below to understand the implications. In this case, it's a barn with tons of airflow over the timbers. If this was a barn conversion, however, insulated at rafter level, there would be more and worrying implications. Junctions are vulnerable to water ingress and entry. So are disruptions in the roof covering. There are 3 chimneys through this thatch roof. The brick one has a mortar weathering at the junction between the thatch and chimney. That mortar needs to be reinforced or it could crack or break away as the thatch settles. Lead aprons, however, can be adjusted when that settling happens to avoid water getting into the junction. Chimney tops are also important. Ask the question, can rain get in? Is mortar flaunching in good condition? Also, understand vernacular roof details and traditions and why they work. This Cornish mortar bedded slating uses mortar, but only at the bottom of the slates. It's a measure against wind uplift. Otherwise, mortar, if taken higher up, would form a path for water entry. So it's important to record and understand such details before removing them in stripping the roof. And the vernacular method of guarding against wind-driven rain under the tiles or slates, full torching under the Cornish slate roofing in the centre. Look for damp staining or problems in the loss of plaster on the right-hand side. The left-hand side shows a stone slate roof being investigated. If water is in your roof timbers have to be suspect and need investigation, and there may be secondary defects such as rusting of iron nails, which, when expanding whilst rusting, may affect either the batten to rafter or tile fixing to battened connections. Walls, and a good excuse to put 2 fun slides in. On the left is a window in the base of a Saxon church tower. It's deeply recessed. The survival of lime finishes is testament to how sheltered and protected the window has been. This tower has earth-based bedding mortar, and I'm certain it was rendered. The window treatment provides the evidence. Without render, think of all the ledges for water to sit and be blown back against the tower wall that exists. Sometimes the question, what to do, is answered by the building. And on the right is a Le Corbusier 1930s design, but constructed in the 50s, drip mould, which takes runoff from the wall and discharges it onto the grass of the flat roof. I just love the scale. He really meant it. In the southwest here, they'd call this detail a proper job. And sticking with vernacular, southwest vernacular, the epitome of vernacular wall detailings for moisture is this cob cottage on the left, with a good hat and pair of boots, or overhanging eaves and masonry plinth, to keep the cob away from the moisture at ground level. Just going off script, you should be aware actually that environmental buffering characteristic of Earth is being considered and recognised as state-of-the-art environmental buffering. And check out the Ricola Herb Throat Lozenge Company in Switzerland, choosing earth as the material for its external and dividing bay walls for their new mass storage facility for herbs. Matt has a link for you, I think. And 2 examples of vernacular wall treatment to shed water. The West Sussex galleted flint work, where the flint gallets break up the large amounts of mortar between the flints. This reduces the risk of shrinkage, but also gives the wall thousands of drips from which to shed water. And on the right, slate wall hanging as a second barrier on the external sea-facing elevation, again bedded in lime mortar. Now, we need to talk about rainwater management. The principle of rainwater management is to capture the rain at roof level and safely remove it well away from the building at its base, causing no damage in between. Some examples of rainwater removal from roofs, therefore. Clockwise from the top, a jumble of junctions. The ideal in this situation would be to provide good lead flashings that discharge the water into hopper head, like the detail below. See the pipe towards the top of the hopper? This is the overflow, in case the downpipe or hopper gets blocked, a well-considered detail. The central image is the officers' barracks at Brest Castle in Brittany. I'm slightly worried about the small size of the spouts coming from the gilded lions' heads. Spouts worry me generally, as so often wind blows the water back onto the building. Top right, water from upper roofs usually discharge direct onto lower roofs, but they've worked really hard here to avoid this. There is a problem, however, at the eaves. It doesn't quite discharge into the hopper. The more usual arrangement is beneath, where the upper downspouts discharge onto lead flats and then into valley gutters and then into downpipes. Again, take your ladder and get into those valley gutters and walk along them, looking or feeling underfoot for give in the timber gutter base to get a clue of the soundness, checking for ponding, splits in the lead or defective flashings where water could get in. The sizing calculations for gutters and downpipes are based on surface area and pitch of roofs, and the calculation also includes a factor for rainfall intensity found on rainfall intensity maps. The Met Office climate change predictions, however, indicate an increasing number of high volume or rainfall events that once in a 50-year event designed for may become more frequent. Gutters may need to get deeper and or the number of size of downpipes increased. While we're taking climate change and the link to carbon use, don't forget that porous building fabrics in equilibrium, when moisture ingress is in balance with moisture release, is not wet. It's wet building fabric, however, that transfers heat, costs more to heat, and to provide comfortable conditions and uses therefore more carbon. Another good reason why wet buildings not working well cost money. Downpipes, the journey to the ground. This is a new lead rainwater goods on the first two slides, but you'll see the damp staining and characteristic fan pattern of water created by water from above before the new downpipes were installed. A key maintenance issue is the ability to get to the back of downpipes if they're cast down and need painting. Ideally, they need spaces to keep them off the wall to allow decorators to get behind. And at the base of the very same stone wall, the downpipes are buried within this very grand stone casing. It's a nightmare from a survey point of view because we can't see what's happening. The right-hand slide illustrates when things go wrong. The top of the roundel is where the pipe taking the water from the path above pierces the wall and runs in a curved pipe to the hopper. Rainwater goods collect water, but when they go wrong, they concentrate water and therefore concentrate damp problems. You can see the resulting damage. And the base of downpipes, where they discharge, is important and usually not given enough thought, considering more water is gathered in them as you go down the building. Top left shows a downpipe discharging above a brick drainage channel, splashing back onto the wall and tracking down through the crack between the wall and the channel. In the centre slide, I wonder what happens beneath the hole in the pavement. Out of sight, out of mind is a concern when surveying for damp. You need to know where the water is going. And ideally, as in the bottom left image, you have a canal handy. On the bottom right, finding this on site suggests you've got a roddable, later falls drainage system. And if it was a French drain with geotextile filter layer to stop the silts building up, it would also need maintenance. You need to clean through annually and check all is working well. Ideally, place French drains a bit further out from the building, so if they block, they don't create a water reservoir next to the base of your wall. And turf adjacent to your walls will work
I
better
put
than
the question
gravel.
in there, and people answer.
Now we have a question. Lovely. So the question is, which walls of these four going from A to D, E even, across the top, A, B, C, D, E, are coping best with dampness, do you think? It's clear that all the walls have some form of dampness, so there is a raised moisture content, and the source would need to be found, and we would
In all
need to be
fairness,
happy that it
Nikki,
had been
I've set
addressed.
this as a multiple choice, so they can only vote
And in
for
all but
one.
image
Should they be
D,
able to
we've
vote
also
for
got
several?
salt contamination.
Oh,
So
okay. Well, I'll tell you what.
people are
Let's.
still voting.
No. I will turn that into a multiple answer question. There you go. You can all now vote for as many as
Oh,
you like. There you go.
yes, but don't worry. That's my fault for not making it clear.
Yeah, they all look pretty shocking, don't they?
Oh, wow.
Okay, we're getting a good spread there now. Let's reveal the results. There you go.
Guess that was a really hard question, actually, if they could only pick one. I think even I'd be hard pressed to pick one. And I know the answer. Okay, so let's talk through these. So salts may be present. An example from natural pollutants such as chlorides from the sea, sulfates from the ground, or man-made such as cement, or as a result of the building's use such as gunpowder or road salts. Water has the ability to dissolve these salts, and during normal capillary draw of moisture, the salts, which are now dissolved in solution, are drawn to the external wall surface pores and deposited as efflorescence or crystals when the water evaporates away to the outside atmosphere. If, however, the surface pores of the mortar joint are blocked by non-porous cement pointing, the normal capillary draw of moisture will be halted. Instead, the salts in solution will move to the more capillary preferable porous brick. Also, the change in phase of the salts from being in solution in water to being in solid crystal during evaporation of the water will happen on or within the pores of the brick surface. And a cycle of dissolved solution and then evaporation and deposit as efflorescence in surface is especially damaging, as salts are hygroscopic, so they can take moisture from the air as well as reacting with liquid water. And so the dissolution into a solution and then re-evaporation to continue the cycle and in moisture-laden conditions. And continuing of this process will cause the brick spalling and eventuate deterioration as found in E. So E is dealing with the moisture worse, but B may be at the start of the process. In A and C, the salt is occurring on the mortar joints, which is just what we're looking for. It's just what we need, and it indicates that the mortar joints of the walls are porous enough to cope well with the excessive moisture or damp. But what about D? Yes, the moisture has been taken into the joints, but the extent of moss does indicate a huge extent of dampness to sustain the moss growth. And I'd be worried there that there's so much moisture that there might be a risk of frost. So actually, the mortar joint that is doing best in terms of salt efflorescence is in situation C. You've got very softly hand-thrown bricks there, and they're being protected by the lime mortar. I hope everybody's happy with that. Moving on from salts and brickwork. Below ground rainwater removal can also be important. I just want to make the point here that it's important sometimes to actually dig up and look at where the water goes. Just because you've got drainage may not mean that it's actually running away. And ground levels are important, and to actually understand the difference in level between the ground floor internally and the external ground level, take a datum such as a windowsill and actually measure. Just wanted to make the point with the Brighton Pavilion, the importance of documentary research and understanding even before you go on site. I'll just read you the wording of the interpretation panel in the centre here at Brighton Pavilion. It says, iron cladding from Nash's building. Rust made the iron expand, loosening and cracking the render, allowing yet more moisture to penetrate. I'm just going to speed up. I haven't got many more slides, but I'm aware that we need to get to Sochi. And beware of alterations or extensions to buildings because they may produce a joint which may open up as the building settles differentially. And beware of buried timber. You'll see that that string course on the left-hand image has dropped, indicating there's a problem with the timber lintel behind. The importance of maintenance doesn't need to be shared here, except to think about actually how maintenance is carried out and beware high pressure water equipment and the impact they may have on the building fabric. And then we need to get inside and look at internal signs of dampness and what it's telling us. Remember, the cause of the moisture needs to be addressed, or confirmation that it can be addressed needs to be sorted first. And then what are the signs of damp telling you? So from left to right, water staining and salt deposits on this Edwardian plaster cornice. Is it old or is it ongoing water? Remember, salts can continue to effloresce for some time after the source of moisture has been removed. Its location points to a blocked or leaking gutter or a need to improve the external details. Similarly, below, the junction between wallpaper and the lined out ceiling suggests the gutter junction needs to be investigated if it continues to get wet during or after rain. In both examples, buried timber supports or rafter ends need checking. Removal of boards here may not be an issue, but to investigate timber structure behind plaster or panelling, a non-destructive method of determining soundness of timber is a Cybet drill that makes only a 3mm hole. It's a tool specialist timber decay consultants may use and was actually developed to measure decay in standing trees. In the third example, the dampness follows, obviously, the leaking down pipe externally. And in 4, we've got a window seat with a rotten timber seat, a result of not enough wall thickness here to cope with capillary draw and retention of moisture until the external conditions improve. And finally, the salt and algae affected window head in a damp church tower is the accumulation of liquid water that has percolated down to the window head. The impervious glass and reduced temperature and saturated vapour condition are also contributing to the salt deposition cycle. Soki's mentioned thinking about plumbing, so I won't cover that. Just to make mention of windows, of course, they are a weak point in our thick building fabric. The furthest right image shows monitoring of a stained glass church window that takes the brunt of rain and wind and the risk of corroding glass or embedded metal ferramenta. Since the temperature of glass and metal fluctuates easily, windows often suffer from condensation, and this could be a serious problem if the building is damp or has poorly designed heating. We've got guidance on stained glass and buffering from environmental conditions. I should mention that the role water plays in the decay process of material is covered within each of our practical building conservation volumes. And the information covered in this section of the webinar is also covered in much greater detail in the building environment volume. And then finally, looking at what's happened to the building that's entrapping moisture. The building on the left is a timber frame building behind that cement render. It wants to move and it's cracked and water is entrapped. The next building is crying out for render. The stonework above the window has been painted with an impervious paint and moisture is being trapped. And the final two images are the same wall of a church with cement pointing. Moisture's got in and actually water is literally pouring out of the base of the wall. And this is my last slide. The church tower is the church tower at Chalacombe in Devon, and it's what success looks like, remembering that survey and investigation is the first stage in a successful project. And also this wonderful alabaster monument is from a church in Berkshire. Taking the tower. Several years after repair, the church tower and interior environment is dramatically improved. The programme of work included addressing and making sound the roof and rainwater goods, lead protection to decayed stonework drip details, identification that was penetrating rain that was causing problems and the damp, and then crucially drying or halting the water flows through the walls when the building was scaffolded and sheeted was in place for over a year, during which time the monitoring and drying was undertaken, and then finally repair was undertaken in porous lime pointing, render and lime wash. One final thought before passing to Soki whilst looking at this beautiful monument. Water from above at the wall junction has caused dampness to this wall. Behind a non-lime plaster, salts have mobilised and are trapped, and expansive salt efflorescence pressure has spoiled the finish. She should be concerned also about iron fixings holding her alabaster monument to the wall. Just as a sacrificial poulticing border of porous lime materials works to protect wall paintings on a wall at risk of damp, a porous non-hydraulic lime plaster here would keep the moisture away from the vulnerable monument. It would also poultice residual salts. And here you need to take the building user with you. Explain that new salts will appear on their newly paid for lime materials, but that it's working well. New salts are not a defect, but a good sign of moisture going where it should. And if you take home one point from my half of the presentation, it's this. Water movement in porous materials happens via capillary draw or suction, but it's working at a tiny 1 to 2 micron level. It's so tiny that the pores of some stones are too large and water molecules cling only to the surface of the pore during its movement within them. Water has a preference for pores of around 1 micron size. That's the ultimate size for capillary draw. And here's the thing. The pore structure size in calcitic or lime material is about 1 micron. So it's optimal for water transport. And that is why non-hydraulic lime materials are the most efficient material to use to try and redress modern interventions when we're considering solid external walls built with porous materials.
Nikki. I will try and sort of like go through
Think
the
of it when you see a traditional building.
So why measure moisture? Often we're interested in measuring moisture because of some defect or after some catastrophic event such as a flood, or to locate the source of moisture, or to understand conditions before an intervention. Methods of measuring moisture are suitable for different ranges of moisture conditions. Some methods are only used in the hygroscopic range for assessing inherent moisture, and others are better for assessing liquid water caused by an active water ingress. And then there are a few methods that are good at doing both. So how to decide which is the most appropriate method or methods to use? Here are some of the things that one may think about before setting out to measure moisture content. The ideal approach is to think about the building as a system: fabric, landscape, climate, orientation, and its use. With that in the background, you should ask yourself the following questions. What is the problem? Do I want a quantitative measurement, or will a relative measurement be more helpful? Can we do destructive measurements? Is that possible? Is the building listed? Do we want spot measurements, one-off measurements? Is that sufficient, or are you interested in long-term changes? And are there materials that might interfere with the measurements, such as salts or metals? There are many ways to measure moisture. Some are destructive and others are non-destructive. They can measure moisture either directly or indirectly based on a variety of physical phenomena and scientific principles. These next two slides show a possible thought process to help you decide which method or methods of testing are suitable. And I haven't put on all the measurements instruments that you can use, but just a selection. Often a combination of methods are used in practice to validate readings and to allow investigation in more detail. A further consideration is whether you need to know the absolute moisture content, or will a semi-quantitative or qualitative understanding be more helpful? The majority of techniques are semi-quantitative, meaning that they can relate readings with relative moisture content of materials, and these are recommended to be used comparatively. However, if calibration of these techniques are possible, readings can represent actual moisture content. In addition, different techniques are available depending on your assessment strategy. So, are you looking for changes or long-term trends? Do you need to do just a quick check, or do you need to scan large areas to help locate the problem? So, gravimetry is the most accurate way of determining moisture content in materials, and is often used as a benchmark for comparing all other methods for calibration. In most instances, gravimetry is unnecessary, unfeasible, and sometimes not permitted, as it requires a sample of material to be taken by drilling. It also requires basic lab facilities, and the results are not immediate. The test method involves taking a sample of the material, weighing it, drying it in an oven, and then re-weighing it from time to time until a constant weight is achieved. The difference between the dry and wet weight then can be used to calculate the absolute moisture content. However, it isn't suitable if you're interested in long-term changes such as drying, but rather it can give you a baseline value that you can take with you before you start long-term monitoring. The main thing you should be aware of when you're actually taking a sample is that you use a low-speed drill to minimize the drying of the sample by heat from drilling, and that the samples are immediately placed in airtight bags and weighed. A carbide meter is another way of obtaining absolute moisture content. It's a chemical method from which moisture content can be assessed on-site from drilled samples. These samples are placed in a pressure cylinder along with calcium carbide. Any moisture present in the sample reacts with the calcium carbide and acetylene gas is formed. The amount of gas formed is directly related to the amount of actual moisture found, which then can be read by a pressure gauge. This reading is far more accurate than electrical moisture readings, as it eliminates salts. However, on-site measurements only gives the total moisture content, and the proportion of capillary to hygroscopic moisture cannot be determined. It's also messy with the disposal of the carbide powder, and the powder often expires quite quickly. Again, it's not suitable for long-term changes. A word of caution about materials. When Brian Bridout gravimetrically measured the moisture content of 3 courses of brick in one wall, he found a range of content values, moisture content values, from less than 1% to greater than 6%. This indicates the variability and the heterogeneous nature of traditional materials. It also indicates the difficulty in relying on sampling despite its accuracy. If you are using this method, it is probably advisable to take more than one measure if that's at all possible. The following case study is an example where gravimetry was used. At Buxton Pump Room, we were called in to determine the cause of continued moisture ingress. Given that remedial work had already taken place, our initial theory was that the current damage might be a consequence of slow wall drying, in which case the walls would be damp rather than there being continued water ingress. Samples were taken by Ridout Associates on the northeast wall below the cornice level. The red circles indicate measurements taken of the damp areas, and the green circles indicate measurements taken from dry areas as a control. Analyzed by gravimetry, they confirm the presence of liquid water and ongoing moisture ingress. When the roof was inspected, we found that the flashing detail was installed incorrectly and not as shown in the specified drawing. It appeared that rather than inserting the zinc flashing into the parapet higher up and covering the asphalt joint, it had been by mistake packed into the vulnerable joint, allowing moisture ingress to continue. If you don't know where to start, but you know that there is a problem, scanning techniques can be a useful first step, as it can look at large areas at a glance it is non-destructive. Infrared thermography is non-destructive, non-contact surface technique that captures the heat energy emitted from the surface of the object. This technique is based on a temperature difference. So when there isn't a sufficient temperature difference, no thermal contrast can be seen by the camera, and that is shown as an example in the first hazy green image on the left-hand side of your slide. There are two forms of thermography, passive and active. Passive thermography captures the natural thermal patterns of a surface where the blue and purple areas are cold and the red and yellow areas are warm, as shown in the top thermal image. The image here identifies a continued damp problem on the right-hand side of the wall, which is in fact due to a faulty chimney. The active thermography requires energy, either heat or by cooling, to create temperature differentials. If you look at the bottom thermal image, you can see that this method can sometimes be used to locate subsurface moisture, for example, to diagnose roof defects after a warm sunny day, as water has a higher thermal capacity than most building materials and retains heat for longer. In this instance, wet areas will appear warm and dry areas will appear cold. Here at Carlisle Castle, thermal imaging helped to identify location and confirm that the source of the moisture ingress in the keep was from a defective roof, though this was actually already known there was a defective roof, but we were partly called in to provide some additional evidence to fund the work. The yellow areas suggested that there were voided spaces beneath the flagstones that may possibly contain water, and that the lower part of the parapet was very damp. As you can see in the thermal image, water was channeling down the parapet junctions and pooling around the edge of the roof. IR thermography is a powerful tool, but sometimes can be difficult to interpret. If done incorrectly or when weather conditions are not appropriate, the results can be misleading. What may appear to be moisture may actually be missing insulation, air leakage, or other deficiencies unrelated to moisture. Weather conditions and having a sufficient temperature differences are particularly important, and there are other conditions that you should consider. And there is a separate webinar on infrared thermography in this series of survey and investigation that, if you're interested, you can go and have a listen to. So I won't say any more about thermography. The microwave moisture meter, these measurements are based on the dielectric permittivity of water and the surface geometry of a material. Subsurface information can be revealed at a range of depths from 3 to 80 centimeters and is most reliable as a comparative technique. Non-destructive sensors and an invasive probe, which is inserted into a drilled hole, are available. The technique is useful because it provides a spatial distribution of moisture. It's not affected by salts and is effective to measure rapid drying, such as after a flood. However, some materials such as metals and also voids and rough surfaces can interfere with the readings. It's generally not advisable to use the device for absolute moisture content unless the specific calibration values of the material are known. And the manufacturer, they do provide generic calibration values, but we would recommend that you do not really use them. The technique is not widely used for surveying buildings, as it is mostly used in science and for specialist investigations, but we have found it quite useful. Here at Bridport Literary and Scientific Institute is an example of using a combination of techniques, as often in practice not one technique is completely reliable, and that you need to be able to validate your readings as well. A new render had been applied in 2017 on the west elevation. However, on drying, it exhibited a pattern of unsightly pale and dark areas which seemed to change over the course of the following 2 years. In addition, a fine network of cracks surfaced which, if not remedied, could cause problems in the future from moisture ingress. We were asked to investigate whether a relationship exists between the pale and dark areas of the render with moisture content. IR thermography was used to produce a thermal map of the surface temperature of the west elevation. This was to look at the difference in surface temperatures across the elevation to determine where moisture was present. However, we found that the pattern of moisture distribution in the render was difficult to determine as the heat loss from the chimney flues influenced the thermal image of the render. Nonetheless, we thought it was possible as the building was heated, and if the render was damp due to the higher heat capacity of water, the lighter yellow-orange colored areas in the thermal image could indicate presence of moisture beneath the surface, but not obviously the pattern where you see the flues. With the microwave moisture readings, it seemed to support this analysis. As you can see in the bottom right-hand corner, we took some measurements with the meter, and the darker areas in visible light were damper than the paler areas, which is shown by the light blue, which is supposed to be dryish, and the darker blue, which is supposed to be damper. On the south elevation, without the influence of the heat loss from the flues, we sprayed water on the network of cracks, increasing the temperature difference between the cracks and the surrounding area. The thermal image picked up the network of fine cracks, suggesting that the patchy appearance of the render was actually due to moisture seeping into the render. So bear with me with this slide because this is a bit difficult to understand, but hopefully you'll understand after I've explained the following slide as well. So these two graphs show readings from the microwave moisture meter using a non-invasive sensing head and a long probe for invasive measurements at Kenwood House, where there was a problem with moisture ingress on the northwest walls of the orangery. Without going into detail, the image on the left from the sensing head indicated that the walls were actually dry when in fact they were very wet in the corner, whereas the probe correctly identified the wet and dry areas. It seemed that there was an impermeable layer of plaster on the northwest wall, which was interfering with the readings from the non-invasive sensing head. Thermal imaging revealed that sections of the north and west walls have been possibly replastered, as it exhibited a different thermal temperature from the rest of the walls. Indirect destructive techniques cannot be as accurate as the gravimetric method. However, they can be useful, particularly to assess changes in moisture conditions over a period. There are several options available, which all requires holes to be drilled into the masonry to insert probes. Some of the methods, electrical, resistive, and relative humidity and temperature, can be set up in the long term to monitor in the long term with data loggers. Timber dowels can be used as a proxy material to assess the relative moisture content of walls. The dowels are left in the wall to equilibrate to the fabric, and then they are periodically weighed and dried. If this is repeated over several months, a long-term picture can be built up of the moisture conditions of the wall, and this was the method that we used in that church tower that Nikki referred to in Challicum. Others, using the long probe of the microwave moisture meter, can only be used for spot measurements, but it can give you a depth profile through the wall. A protimeter deep wall probe can be useful, but also is problematic as sometimes it can give you false high readings if salts are present. For long-term monitoring, we mainly use timber dowels or timber blocks embedded with stainless steel screws as resistivity sensors combined with relative humidity and temperature sensors. And here we've been monitoring in this house for about 7 years at the wall insulation interface to assess moisture risk after fabric upgrades. The most commonly used methods are electrical techniques, resistance and capacitance. Resistivity meters use electrical conductivity of a material which is related to its moisture content. They have 2 contact pins that are pushed against the surface to measure the conductivity of the material between the pins, but good contact is required. They are useful as a quick check, they are clean and non-destructive. However, these commercial meters are problematic for masonry materials as they are calibrated for timber. Therefore, the readings with other materials can only be used for comparison. Another problem is that the presence of hygroscopic salts and metals will affect the readings and will give you a false high reading. They also are unreliable at high moisture conditions as they are sensitive to the presence of free water. Nonetheless, if you use them sensibly by taking a series of vertical readings in order to obtain patterns of readings, it can give you some comparative useful information. Of the two electrical techniques, capacitance meters are generally better for masonry materials. Capacitance is a measurement of the dielectric constant of a material, that is, its ability to hold an electric field. Water has a very high dielectric constant, approximately 80 at 20 degrees centigrade. By contrast, dry materials have dielectric constants of less than, dry building materials that is, have dielectric constants of less than 5. So capacitance is proportional to the volume of water in the sample. However, salts can still interfere with the readings, though to a lesser extent than the conductivity meters. Rough surfaces also introduces some uncertainty, and how you handle some of these meters, like the one on the far right, the black and orange one, seems to have an effect, as we found that depending on the pressure applied, the readings also can vary. This type of a capacitance meter is best used under its own weight rather than applying any pressure. Obviously, that's not possible to do on a wall, and is only possible to do on a floor, which is what we're doing here. In that instance, it's advisable that the same person carries out the investigation for one case to minimize inconsistencies arising from different users. Or you could test it out to see if the values change depending on the amount of pressure that you apply. So we've been doing some research, which I won't go into today, but as I said at the beginning of our talk at Historic, we're often asked to provide advice on damp problems. Whilst there are many different methods available, all have some drawbacks. This work will be published soon. We're sort of kind of drafting it at the moment, but there is a short article on the link below there, which for some reason you can't really see very well. But Matt can send that to you afterwards. There's little agreement over how they should be used and little information over how they compare with one another. So to try and understand this better, we commissioned Oxford University to provide an intercomparison of the performance of different methods of monitoring moisture in key porous building materials. We tested 12 non-invasive and 5 invasive moisture methods. Just briefly, key findings are that most methods tested can give a good semi-quantitative estimates of moisture levels, though some performed much better than others. Range was a limiting factor for some meters, where they were only reliable over a very narrow range of moisture contents and very unreliable in damp conditions. The performance of the meters varied depending on the material, and we tested a range of sandstone, limestone, brick, and lime mortar. And we found that a combination of using the microwave moisture meter and the timber dowel method was effective to monitor drying after a flood. So just to end, just a word of caution: many meters only have relative or arbitrary scales rather than percentage moisture content by weight. In other words, the meters may display values from 0 to 100 or 0 to 200 or even into the thousands, but these do not refer to percentage moisture content by weight. Instead, they are simply non-absolute indicators of higher or lower moisture content. And each manufacturer uses different relative scales for the same moisture content, which adds to the confusion. For example, you may get a reading of 50 on a scale of 100, and on another meter you may get a reading of 100 on a scale of 200. But that doesn't mean conditions have worsened. They're both still at around 50%. It's problematic as the value of the measurements are really dependent on the experience of the user to interpret the results, and also interpreting between survey measurements. Let's say if you're drying out a building in a flood and you have various different people coming into the building on a monthly basis taking measurements, that you can get quite different results by different practitioners. As already mentioned, there is no standardization of how you use the meters, i.e. the pressure applied, the depth of penetration. You must remember they cannot be used to compare between materials, and because of the variability of traditional building materials and that most buildings are composite structures, this also adds another level of complexity in terms of interpreting the results that these meters provide. So now I'm going to hand over
Thank you,
back to
Saki.
Nikki,
Just
who
one
will conclude
final
our
point to
talk.
make, and that is a document, a working draft that's in production. It's a really good document. It's about the investigation of moisture and its effect on traditional buildings. So absolutely chimes with what we've been saying today. And it's a joint document between the RICS, Property Care Association, and they're the commercial damp surveyors and contractors. Historic England, but also Historic Environment Scotland and CADU, etc., are signed up to it. And the great thing is that it absolutely adopts the importance of understanding the building and moisture movement in traditional buildings, that those of us who are advising owners or contractors or professionals in the field would support. So that's the final point, and thank you very much for bearing with us as we've gone over. Thank you.
Nikki and Soki, thank you so much. Absolutely fantastic presentation with so much information there for everyone to take away. Before you all go, I know we've run over time, but I'm going to put this in front of you guys. So any questions? If you have any questions for our presenters, please put them in this window here, and we will field those over the next few minutes. I also have this window here, which if you click on the actual title, feedback, webinars, etc., you will see the URL appear at the bottom of that window, and then you can navigate to those resources after the session. Right, I can see questions coming in, so let's have a look at some of those. Yes, slides will be made available to you afterwards. Thank you very much. Does Historic England have a fixed position on lead chimney flashings versus lime fillets on thatch?
I can take that, yeah.
Oh, go on then.
Well, absolutely not, because with all details in buildings, there are vernacular traditions, and it's really important that vernacular traditions are followed first and foremost. I didn't say that you couldn't use mortar, but be aware that with the settlement of the thatch, that you may not have the tight joint that was there originally.
Brilliant. Okay, thank you. There was there was one in that I think this is sort of the same. Does no, that's the same question in the chat room, isn't it? There was another question I saw in the chat room earlier. Someone was interested to note that we promote lead cover flashings on drip that will direct runoff to areas below faster. Is that a similar sort of question?
I can take that. Remember that drip moulds in walls are built into the structure as the building is built. So actually they'll go in quite a way. And you can therefore have quite a loss of fabric if you cut out and replace the stone. But again, it depends on the extent of decay or a balancing out between. The key thing is to get the water drip working. So either piecing in, we aren't against piecing in, but lead can sometimes be useful in retaining more historic fabric than if you try to go for a stone replacement drip detail.
Okay. Is there a way to find out if salts are present to see how they may affect one's survey results?
I think with when you do the gravimetric analysis method, you can there's a step in between which you can do, and you can assess if salts are present or whether it's just free water. But I can't actually give you. I don't know the equation offhand, but it's a well-established method, and I think BRE publish a small paper on this in their digest series. So okay. Yes, it's as an answer to your question.
Someone's mentioned a Bresel patch test can be used to identify salts. Okay, what is Historic England's advice? Moved on rising damp in basements.
You should look at Robin Pender's webinars, because she mentions this in her questions. The problem with anything below ground is that usually we're dealing with walls that are above ground, and airflow as well as sun actually is a mechanism which tracks the moisture and takes it away from the internal face. You don't have that benefit in basements. And there are systems such as an egg crate kind of system that can go on the wall, which in theory promotes airflow over the surface. But again, there is no airflow to promote that. If it was my basement and I was having to deal with moisture, I perhaps would install that. But think about also introducing some air current, so perhaps a hot water pipe along the base of the wall to induce some air circulation or convection. But there is not an easy answer. Please look at Robin's webinar. She's the scientist and she can explain further.
And if you go to that little window to the right of where all the answers are, and it says webinars there, if you click on that, that takes you to the web page on the HE website that lists all future webinars and indeed all the recordings for previous webinars. And you will find links to Robin Pender's webinars on damp there. So another question, is there any limit in height to the extent of capillary rise in fine sandstone when gravity is that gravity or gravity influencing the opposite way? Gravity influencing the opposite way. It is gravity, isn't
it? Sandstones, like any porous material, will have a pore structure that's larger than lime-based material. Moisture will rise, but usually by the time it's got to a couple of courses up a building, if the internal and external faces have non-porous material and moisture is allowed to escape through them, then the rise is actually limited. So it's all about actually on that wall thinking about what is happening, what the issue of groundwater might be, ground levels, what is happening on either side of the walls.
Okay. So we've had a question about basements, but what about structures built above underground water sources? Is there any solution there?
I've seen an example of this quite recently, a cottage in Devon where periodically a natural stream does rise up and floods through the kitchen. So in case there, they've actually built in sump pumps for when that eventuality arises. So you need to understand the likelihood and put in measures to deal with your particular situation.
Okay. Last question then. Any recommendations for masonry? Sorry, Soki, I have to mute your microphone. We're getting an echo there. There you go. Any recommendations for masonry desalination, compress poulticing, where there are severe structural damaging salts or sacrificial plasters? Is that one for you, Nikki, or is that one for Soki?
Is that mine?
Sorry, I just missed the question.
Over to you,
Sorry.
Soki.
What was that? I was...
Okay. I'm going to mute you, actually, Nikki. So we're getting feedback here. Oh no, it is actually Soki. For some reason, we're getting feedback. I'll try and talk over it though. Any recommendations for masonry desalination where there are severe structural damaging salts or sacrificial plasters?
Ooh, that's not really my area, but I know that there are a number of techniques that conservators use to remove salts. One method that I've seen people use are using various different poultices for treating salt damage. I mean, I think before you start thinking about treatment, I think you probably would need to work out what type of salts actually exist, and that you can determine obviously by analysis, but also by trying to understand the source of the water, so whether it's groundwater or whether obviously if you're in along a coastal environment, and that will help you to work out what would be the best treatment. But you would have to really consult a stone conservator who understands treating stone walls, which unfortunately I don't, but I know a lot of people who do. So if anyone wants to email us that question, we can find out.
And just to add to that, of course, with every issue of damp related buildings, you need to find the source of moisture and stop that first. And in terms of salts, it's about putting a more porous material on. So there's a material, for instance, available on the market which is lime render, and has no aggregate apart from limestone dust. So it's purely calcium carbonate when it's carbonated, and therefore will, because of the pore structure of 1 microns, pull moisture and therefore salts with it. Now that will act as a poultice, and it's like to be salt laden, and you need to replace it again, but it will work. It won't be a quick fix solution. I think that's the thing. Taking moisture and therefore salts needs to be thought about and done very slowly.